All right, let's continue. So the scientific method is one of the things that has made science so dominant in our culture, in that we have been able to build, as I was talking about earlier, build facts on top of facts. And this is how we've discovered so much and created so much. So let's go look at the scientific method. And so the scientific method would have these 5 formal steps. So, first of all, you might recognize a question or an unexplained fact about the natural world. So, you might be as simple like, why is the sky blue? And we'll be talking about that later in the semester. But why is the sky blue? Well, the scientific method says the next step would be to come up with an answer, an explanation, an educated guess, meaning using your best knowledge. So I might say, well, the sky is blue because oxygen atoms are blue. So showing my knowledge that the air has oxygen in it. Okay, so it has to be a reasonable explanation. That's called a hypothesis. And one of the things is that a hypothesis must be testable. So you have to be able to perform experiments to test to see if your hypothesis is true, or at least is not false. So one of the ways to do that is to experiment. And to do an experiment, you would have to say, okay, well, what are the consequences of the hypothesis? So you might say, well, if I look under a microscope, would the molecules of air, or at least of oxygen, be blue? If I had a box that was pure oxygen instead of air, air is only 21% oxygen, would that box of oxygen be bluer than a box that has air? Or are there places on the earth where the air has more oxygen? Would that be bluer? So anyway, so you might have some consequences, some ways that you might test it in the lab or by observation around the world. And so then you would perform those experiments. Now, sometimes you can't perform an experiment in a lab. So it has to be an observation. So like right now, we can't put black holes in the lab, but we know where black holes are and we can observe them. And we can make calculations and check to see if our calculations match with what is out there in reality. Okay, so observations and calculations are also important. My husband at Fermilab, that's his job. He does calculations of what the experiment should show when particles enter the detector. And the idea is if you know what you're talking about, then your calculations should match up to reality. Okay, so anyway, so people did figure out why the sky is blue. But it turned out to be more than the idea that oxygen atoms were blue. Um, and so the idea is in the end, you take your original hypothesis and the effects that you found, the experimental findings, and you try to figure out if those can be put together into one general rule. And it turns out for why the sky is blue, there is a general rule. It's not that oxygen atoms are blue, but atoms of oxygen and nitrogen in the air scatter blue light. So that's the light that reaches your eyes from all directions in the sky. So you see the sky is blue. Whereas if you just look directly at the sun, which you shouldn't do, the light is white because it's made of all colors. They haven't been scattered, but the blue has been scattered. So it reaches you from many directions. And the thing is, so scattering is the answer. The light is scattered, but why just blue? Well, that's where the general rule comes in. It turns out that light has one of the smallest wavelengths, and that wavelength interacts with the atoms and scatters. Okay, whereas the larger wavelengths are not scattered easily by just the air. So not by the nitrogen and oxygen. They do get scattered by dust, which is one of the reasons sunsets are red. Okay, so we'll talk more about that when we reach that part of optics. But the idea is that asking that seemingly simple question led to a general idea which had to do with wavelengths of light and the size of the atoms, because the wavelength in the atom size matters if it's going to be scattered. Okay, so anyway, so that's the 5 official sort of steps. Now let's look at hypothesis. Now it's an educated guess, so you use your best knowledge. It has to be a reasonable explanation, is another way to think about it. It has to be answering the question, okay? It has to explain it, and it must be testable. Okay, so let's go look at some examples of this. You've got a homework problem like this and a test question like this. So which of these is a scientific hypothesis? So I've got 4 possibilities here. Now, the first one says physics is the greatest science. That's what we call an opinion. Okay, I mean, I think it's true because I'm a physicist, but it may not be considered true by others. So that's one of the ones that it's not a scientific hypothesis, especially because it uses a word like greatest. Greatest in whose opinion, right? That's definitely an opinion-based thing. However, it's true. But it's not a hypothesis. 2, leaves turn red in the fall because they have an iron shortage. Okay, that's explaining something. And you might say, okay, well, that's something that you could easily test, right? You can test leaves to see if they have a shortage of iron in the fall and test to see how that affects their colors. Now, as it turns out, that is a reasonable scientific hypothesis, but it does turn out to be totally false. So if you were a scientist, you would find that your hypothesis was wrong. And that's valuable because that means that you have crossed off one of the reasons for leaves turning red in the fall. Okay, and then you would keep looking at other reasons. Okay, so in science, sometimes it's just as exciting to find that you're wrong because you're able to then work on other hypotheses. Again, in high energy physics, which my husband is in at Fermilab, what they do is they test different areas of energy. And so they're trying to find particles sometimes, and they test this area of energy. So they have particles in a certain energy, and they say, nope, it doesn't do it there. So they cross that off. And then they test another area, and they cross that off, another amount of energy. And the thing is, what they're doing is circling in, trying to find the correct amount of energy to create these particles. And so that's actually why they had to build a bigger accelerator in Europe, because Fermilab didn't have enough high enough energy to produce what's called the Higgs boson. So anyway, which you may have heard called the God particle. Anyway, so they actually found out, yeah, we have to go to a bigger machine. Anyway, so number 2 is a scientific hypothesis. It just is wrong. And down below actually are some leaves which have had their fleshy parts taken out. And one of the things is that what happens in the fall is the chlorophyll is no longer maintained because the tree is expecting that winter is coming. So as the nights get cold, they stop creating chlorophyll. Sometimes they even suck it back into their trunk. And what happens is that the underlying skeletons of the leaves and other processes produce the red colors. Okay, so it's not an iron shortage. Okay, now black holes are filled with an undetectable substance. Well, it's not really explaining anything. So it's not a very good scientific hypothesis. And especially this idea of undetectable. Well, it's kind of hard to test something that's undetectable, isn't it? As a matter of fact, we have right now scientists doing experiments trying to figure out in space what dark energy is and dark matter. And the problem with those two things is that they don't produce any light. So it's hard for us to get information, and we have to study them by their gravitational effect. So we can't detect them through lights. We can't use normal telescopes, except we can detect the motion of objects around them. So anyway, so it's almost undetectable, but not quite. We figured out how to do it by gravity. Okay, but that's not a very good scientific hypothesis. Okay, 4, we were put on this earth to find happiness. Well, that's sort of what you might call a philosophy of life, but it's not a scientific hypothesis. It would be nice if it was true, but it's kind of difficult to test. All right, so let's go on and look at some other parts of the scientific method. When you've had a hypothesis that's been tested over and over again, and it hasn't been contradicted, then this may lead to what's called a theory. A theory is an important truth about science, the nature. And it's a synthesis of well-tested and verified hypotheses about the natural world. And so one of those theories, maybe you've heard of, is the atomic theory. In the atomic theory, what goes on is that you are saying everything's made of atoms. So you can knock on wood, right? And you know it's got atoms. But you also know that you're breathing in oxygen and nitrogen, and you believe those atoms exist. And you know you're breathing out carbon dioxide, and you know those atoms exist. Because you've been told they do, but they've been proven to exist too. So scientists have verified this, that every solid object, every fluid, every gas, that's made of atoms. Okay, now the theory of relativity, that sounds pretty exotic. That's based on Einstein's ideas, and we'll talk a little bit more about Einstein later. But the idea with the theory of relativity was that Einstein said that, well, one thing he said was that when you go faster, when you're in an accelerated space, time is different. So maybe you've heard about the twin paradox, where one twin would go off in a spaceship, and when he returned, he would be younger than the twin that was left behind because he experienced time at a faster rate. Well, recently NASA actually sort of did a twin experiment where they had one twin astronaut who stayed on the ground, and one twin astronaut was in the International Space Station for nearly a year. However, they didn't really expect to see any difference in terms of aging, except as differences of the body. But they have tested this experiment, not with twins, but with clocks. You put clocks on airplanes, zoom them around the world. When they come back, the clocks that used to match them on the ground now have different times than the ones on the airplane. And part of Einstein's theory had to do with gravity too. You can put a clock in the basement of a tall building and in the top of the tall building, and if it's a really good scientific clock, which is called an atomic clock, then it will actually have different times. So anyway, so actually it was proven with clocks and airplanes and not with twins. Okay, the twin thing was mostly to see how their bodies would react when one was in space for a year. And there's always a lot of muscle loss when you're in space and other things. Okay, so anyway, we'll talk a little bit more about that another time. Now, the theory of evolution. One of the problems is when people hear the word theory, they tend to think that the word theory just means idea, because we use the word wrong. We say, oh, I've got a theory about that. Even scientists do it. You know, you've got a theory about why Tim won't shake hands with Lou. Okay. That's not the scientific word of the word theory. A real theory, a scientific theory, had to be proven over and over again. So when we say theory of evolution, we're not just saying Darwin had an idea and nobody's done any research on it since then. No, it's been proven over and over again. So, the fact that you're out there and you're trying to decide, do I want a German Shepherd pet or do I want a corgi? Humans have been breeding animals for years to have different genetic variances. That's part of evolution. Except natural evolution is that you have forces from the outside that change things. So, forces in nature. And the animals that survive these forces, too much sun, not enough water, then radiation, whatever happens, those forces, the animals that survive will fill their ecological niche as long as they can. Over here, I've got a little fella. This is a trilobite. And this trilobite, we don't have these anymore in the world, except as stone fossils, because they all died out 230 million years ago, way before the dinosaurs. And so the Great Extinction, which we'll talk about when we talk about climate change, that too was due to climate change. Not caused by man, but caused by volcanoes. Anyway, back to this. So the theory of evolution, let's look a little bit at that, because that was an experiment that was performed accidentally. I mean, Darwin had ideas, right? And those were great. And then there was an accidental experiment, because sometimes experiments happen by accident. This is one that happened in nature, and it has to do with these little moths called the peppered moths. And you can see how it's called the peppered moth because it's got the salt and pepper wings. But a few percentages of the peppered moth are this black color. Now, what happened was, normally the trees, these lovely birch trees and things in England, the black moths show up and the peppered moths are disguised. And so the idea is that usually being a black moth was not good, because you would be picked off by birds, because you would be seen more easily. Sorry. So anyway, what happened was that England experienced a great amount of pollution during the Industrial Revolution. So we're looking at the 1900s here. And so what happened was there were smokestacks, people were burning coal in their homes, there was no attempt to clean the air. And in London especially, what happened was, because you had a lot of fog, everything mixed into this horrible slurry, and you could not see down the street. This is the days of Sherlock Holmes, and the thieves could run out and disappear into this thick fog, which was part pollution and part natural fog. And what happened was that all that coal soot wrapped the trees and the houses, so everything was turning black. So what happened with the peppered moth? Well, what happened was that the black moths now were better disguisers than the peppered ones. And so what happened was that the number of them totally switched. Soon 95% of the moths were black, and only 5% or so were the peppered variety, because there were evolutionary forces that now made the black moth the better survivor. Okay, but then people figured out how to clean up smokestacks. They started to use natural gas in their homes. And what happened was that the rain came and changed the trees again. So the trees started to wash off and be gray again. So what happened? The population of the moths switched the other direction again. Now the evolutionary advantage was to be a gray moth. And so that's the idea. Evolutionary pressures cause animals' genes to be selected. The survivors are the ones who go on to breed. Now, an on-purpose experiment with genetics happened recently. Well, it's happened over the last 50 years in Russia, or somewhere around there. And what they've been doing is trying to breed a tame fox. Because people have been interested in this idea of animals that are actually tame. So like a horse, okay, that's called a domesticated animal, or sheep or cows. But there are a lot of animals that aren't domesticated, like zebras and giraffes and lions. Those are not really domesticated. They have not gone through the process of being winnowed out for their ability to get along with human beings. And so what they decided to do was, as an experiment, to create tame foxes. And how they did that was the baby foxes, the kits that would be born, they would test them. So they would come up to the cages, and the babies that snarled and yapped at them, well, those would just grow up to become fur coats. The baby foxes that were agreeable to humans, they would get to breed again. So they kept breeding foxes over 50 years, and eventually they came up with tame foxes. These foxes love people. And you've probably seen online, maybe you've seen some of the videos. There's some people who have some tame foxes. They cost about $5,000 if you want to own one. Um, but they're adorable, and but they love humans, and they act a lot like a cat. So anyway, but when they were breeding them, they were just breeding them to be domesticated, to be tame. But it turned out that other genes came along with it, because what Darwin didn't know is that genes are connected, right? We've got a certain number of chromosomes that have genes that are connected. And it turned out the gene for tameness is a modified fight or flight gene, where normally animals would run away in a fearful situation. But that gene was broken. Well, it turned out that that was connected to another gene for cartilage. And so what happened was that animals not only got tame, but they also affected the cartilage. And so their eyes got bigger and wider, their tails got curlier, and they often would have droopy ears, which regular foxes don't have. But you can see all that in a dog, right? Dogs have those big eyes and often droopy ears and curly tails. I have a chow, so he's got all of those things. And so anyway, so it turned out that the domestication gene was connected to this cartilage gene. So actually, tame animals often have those features too. Anyway, so it was something they weren't looking for, but it was a wonderful experiment, and now the world has tame foxes. Okay, now another thing that can happen is what's called a law. So a law is a statement that describes a fundamental relationship in nature. These are really important. So there are lots of hypotheses out there, lots of theories, but laws there are fewer of. And so we're going to be learning a number of those laws, because we're going to be learning Newton's laws, for instance. And Newton's laws of motion. Newton had more laws than anybody else, so Isaac Newton. But the idea of the law of conservation of mass is one that Antoine Lavoisier came up with. And that was the idea that you would have the same amount of mass before a chemical reaction and after a chemical reaction. Now, let's look at this a little more closely. So what did Lavoisier do? Well, one of the things that people used to do in those days was they would check out the mass of things. So as they would do a chemical reaction, so one of the reactions they used to play around with was they would have a candle, and they would put some weights on the other side of this balance thing to match the weight of the candle. And then they would light the candle on fire, and the candle would burn away, and gradually what would happen? Well, on the left side, it would get lighter. And so this would start to tilt. Okay, now Lavoisier came along and he said, hold on, what would happen if we put this inside a glass globe? Okay, so now when the candle was burned, it turned out that it stayed level. So Antoine Lavoisier figured out that gases were important because what's happening here? And so we're going to go over this a little bit because we will be using this occasionally. I'll say, hey, a hydrocarbon, and you should know what a hydrocarbon is. So what's happening with this candle? Well, a candle is made up of waxes and oils. And what those are long chains of carbons. And they have hydrogens on them. So this is similar to a sugar or a fat, any sort of oil, gasoline, and the different length of the chain determines what kind of chemical it is. So like gasoline usually has like 14 carbons in a row. And you know that methane is just CH4, that's a gas. So anyway, but this is a hydrocarbon. And so what happens is when you're burning the wax, what's happening is that oxygen is part of the burning process, right? That's called combustion. So what happens when you take oxygen and you mix it? It has a chemical reaction with the hydrocarbon. Well, oxygen goes in, and what comes out is carbon dioxide and water. Now, you usually don't see the water because it goes off with steam because it's hot. And if you didn't have a globe, of course, those two would just go off into the air. And so the candle would get lighter because the carbons are the heaviest part of the candle. And so by putting the globe on there, he was keeping those gases in there, and he was showing that the mass should be the same before a reaction and after a reaction. And by the way, poor old Lavoisier, he lost his head in the French Revolution. So anyway, people pled with the courts. They said, no, this man is a great scientist. We need to keep him. And so what happened was that the court said, no, we don't need scientists. So then about 3 months later, the French government said, oh, you know what? Maybe we should have kept the scientist. But anyway, yeah, sad thing. He lost his head. He wasn't a noble, but he still lost his head during the revolution. Okay. Now, the scientific method that we were talking about. Oh, I forgot to say something. Whoops, back up here. Okay. Theories may undergo change and refinement as new experiments are performed. Okay, so like the theory of evolution we were talking about, Darwin had no idea about genes and chromosomes. Nobody knew about that stuff yet. And yet, so what happens is now we understand why things happen, like why those domesticated foxes have those curly tails. Okay, so just because it has change and refinement doesn't mean that it's not good science. And it doesn't mean that the theory is wrong. Just like Lavoisier says no gain or loss of mass occurs during a chemical reaction. But it turns out that light is equivalent to mass, as Einstein figured out. So actually, there is a tiny little bit of mass that gets turned into light. But for chemistry purposes, it's still equal. Okay, for physicists, we might get a little fussy about that tiny little bit of energy. Okay, so laws don't have to, they just state the finding, they don't have to explain it. Laws don't have to talk about atoms. So Antoine Lavoisier was able to talk about the gain and loss of mass without saying that there were atoms because nobody knew that yet. Okay. Okay, now, not every scientist follows the scientific method in those 5 steps that we talked about. Sometimes you're coming in halfway doing an experiment and something cool happens and you weren't looking for that information, but you're certainly not going to throw it away. That's part of the scientific attitude. sometimes people are just playing around. So sometimes it can happen from trial and error. So like my husband does, they keep trying this energy level, this energy level, this energy level, this energy level, trying to figure out what energy will cause um, the particle to come into being the way they expect. Um, so there can be trial and error. There can be observations. So, like we were talking about in biology, especially, there's a lot of observation that goes into it. Um, and if you're watching the sky, people have discovered all these weird lightning formations called sprites and stuff like that. Those weren't predicted beforehand. They were something that was seen, and then people had to try to explain it, which is part of the scientific method, right? An unknown thing. But it was the experiment, the taking the pictures of it, that led to this circular idea. You're doing experiments or seeking knowledge, and then you find something cool, and then you have to try to experiment to explain it. Anyway, so yeah, so sometimes people just experiment without a goal. Sometimes it can even be accidental. So we're going to talk about radiation hopefully at some point. And this is one of the famous accidental discoveries, in that some photographic plates were left near a sample of uranium, and they showed a pattern on the photographic plate. But the scientist figured out what had happened to those photographic plates. They didn't just toss them in the trash. So one thing is you've got to have the right attitude. And so science has progressed because of this scientific attitude. Um, and so we're finding knowledge, testing that knowledge, and so that we no longer rely on superstition and unfounded information. At least that's the right idea. So, of course, we've been having all these issues with the coronavirus and people coming up with solutions that aren't good ones, and people worried about vaccines. And so anyway, so there's a lot of superstition and unfounded information still out there that science constantly has to fight against. So let's look at this scientific attitude. So we talked about it a little bit before, but the idea is you have a curiosity, your inquiry, you want to know about stuff. Then you have to do experiments. Okay, science progresses because we do experiments, so we can verify the ideas. Then there has to be openness and communication, right? Science is built fact upon fact. You didn't get a TV back in Ben Franklin's day, right? There weren't computers then. There had to be a lot of stuff in between Ben Franklin's experiments on electricity and you getting a cell phone, right? There had to be lots and lots of experiments and ideas in between those things. I mean, there wasn't even radio communication then, much less microwave communication. There wasn't, there wasn't a screen to look at. So there's a lot of, you have to have light emitting diodes. Those had to be invented. So anyway, so there is a lot of openness and communication that happens, and that makes science progress. Now, another one is humbleness. This is a strange one, you might think, because people always tend to think that maybe scientists are a little bit arrogant. They often, do know a lot. But the willingness to admit error is also a key part of science. And anybody who doesn't have that isn't a very good scientist. They have to repeat experiments, and they have to tell the truth about them. And if they don't, they're not being good scientists because they're not progressing science. There was this one experiment that happened quite a while ago now, but there was this cancer drug that was being tried out on some rats. Now, you can order rats that are prone to cancer. They're all genetically identical, and they all get cancer. And so this laboratory had some of those rats, and then they were giving them a chemical, and they thought they saw progress, that the rats weren't, were getting better. They weren't, the cancer was curing. And so they published their results. Well, another lab said, hey, let's try it. So So they got the same rats and the same food and the same medicine, and they tried the same experiment, and their rats were dying. Okay, so what was going on here? Well, this is one of the reasons that when you took science in school, maybe they made you write out the purpose and the procedure. The procedure is actually really important. I know it's boring to write, but what you're doing is you're making a map for other people to follow. And that's what these scientists had tried to do. They tried to follow the map that the other people had put out. And so what happened was that they they got together. So the two groups of scientists got together and they said, okay, what is different about our experiment? And they went through everything, same rats, same food, same medicine, same dosage, and they figured out something different. In the first laboratory, the lights were turned out at night. And in the second laboratory, the lights were left on. And that's all it took, was that little bit of difference that maybe added extra stress to the rats. And or maybe it was deactivating the chemical going through the thin white skin of the rats. I forget the exact reason why. But they figured it out. It was turning the lights on or off. That was the difference. So anyway, so yeah, sometimes that can happen in medicine, especially because bodies are so complicated. So you hear about some great discovery, some cure for cancer, and then a while later it's just disappeared. That doesn't mean it wasn't good data, but it does mean that sometimes it's not going to survive in the real world. If a little difference in the number of hours of light made that medicine not work as well, then you can imagine what being out in the random world of that humans have, how different it can be. And so that's one of the reasons if you ever take an antibiotic or some medicines, they will say, don't take with orange juice. Because what was happening was that there was this drug, which was very successful in tests. And then when they put it out with the real population, it wasn't helping some people. Turned out those people were drinking orange juice, and the orange juice was destroying the medicine. So anyway, so that was something they hadn't tested for. Still a good medicine, but you gotta not drink orange juice. Okay, so anyway, so science progresses, okay, and it builds. Sometimes there's uncertainty, and that's okay in science. It's okay to find out that your hypothesis was wrong, because then you get to go build a new hypothesis. That is part of the scientific process. So anyway, so this attitude is really important. And I have seen that as scientists work together to figure out what's wrong. So once Fermilab, scientists came over from Europe because there was a puzzle. They couldn't figure out why these particles seemed to be going faster than light. And they brought all their data and they said, look, here it is. What's going on? And they were able to figure it out. Okay, so anyway, so yes, sometimes that will happen in science. And let's hope so. I've got a little bit here on Rene Descartes, because he was an amazing guy, but he is sort of the one who helped develop this scientific method. So he figured out by deductive reasoning, okay, which is when you base things on facts. So his rules were: accept nothing is true that is not self-evident, divide problems in their simplest parts, so that's like doing an experiment, solve problems by proceeding from simple to complex. So again, in experiments, we usually isolate one thing that we're looking at, and then recheck. And that's why scientists are supposed to recheck their data and have other people check it too. So anyway, so this was part of the rule, what became the scientific method. Okay, so just the last little bit here. Science does have limitations. Science is about the natural world. And we can test it and explore it using our five senses. So the five senses, right? Your hearing, your touch, your seeing, your smelling, your tasting. Those are our five senses. And those can be used in science. So, I teach some geology stuff, and of course, sometimes you taste rocks or you feel rocks to identify them. Okay, so yes, so those are still used. We often use mechanical extensions like telescopes to improve our eyes, and we have telescopes that can see infrared and ultraviolet and X-rays. So we can expand our range of what we can see. We have devices that can hear an ultrasound, right, and infrasonic, so frequencies higher and lower than we can hear. And so that's the idea, is we've actually built devices that use those same ideas but are more sensitive than just a human. Now, the word supernatural actually means above nature. And so science studies nature. And sometimes people think that science and religion don't get along. But that's not necessarily true, because they do have different purposes. Science is about exploring the physical meaning, okay, the physical phenomena, right? So the laws of nature. We scientists really believe there are laws. Whereas religion is about cosmic meaning and purpose. And you might say that religious people really believe there is a meaning to our existence, that we have a purpose in life. And certainly having a philosophy of life is very important. Knowing what is a good man or good woman, and what does it mean to you? Are you going to follow rules for a reason? And what rules are you going to follow in your life? So, yeah, so having a philosophy of life, even if it's not exactly a religion, is very important. So religion is about cosmic purpose. Science is about cosmic order. What are these rules that we can see out there, like conservation of mass? Okay, and then there's art. So I tend to play around with all three of these. Of course, I do science, but I also am usually doing the rummage sale at my church. And I'm also an artist. But that is your own give back to the universe. Every person's different. Every person's going to take a photograph a little bit differently, or paint something a little bit differently. That's our own interpretation of the universe, our expression. My philosophy of life is that we were born to be creative, and so that is our heritage, is to create. So anyway, so I hope that you will um, find your own philosophy and your art, and of course, science. Okay, now, so that's a great ending slide, but there is one more. So the other thing that we sometimes get confused on is, what is science versus technology? Technology is the practical use of science. Okay, so knowing that I was talking about how we got to a cell phone or a computer, well, there was a lot of technology as well as a lot of scientific laws that had to be developed. So people figure out um, the ideas about how light can be produced from materials. And then that turns into the light emitting diode. Somebody has to invent it. So at first, a scientist in a lab has figured out how to get light out of a material. And then they make it into this thing called a diode, which is what your LED is. So anyway, so the technology is taking the science facts and turning them into practical objects. And of course, it can be helpful and harmful. You might think of something like the chemical explosion of dynamite, and that's a chemical reaction. And so somebody had to invent nitroglycerin. But the thing is, it can be both helpful if you think of it as blowing a road, as helpful, blowing a mountain to build a road, but of course also harmful, because of course it's been used for many other things. So gunpowder and so anyway, so humans use technology. Guess what? We're responsible for how it is used. So you have that legacy, and of course we're going to talk about climate change. There's a lot of technology we figured out, like how to burn fossil fuels. Um, and that makes us responsible for how we use it. Now, we can solve a lot of current problems. The energy crisis, okay, getting energy that is clean instead of energy that is destroying the world. So that is part of it. You may not think of it as a crisis because there seems to be plenty of gasoline around, but the idea is that they had to dig for oil. They have to squeeze it out of rocks now, out of shale. And then it has to be brought by pipelines. And, it's not simple. It's not just Jed Clampett shooting his gun at the earth and when oil comes bubbling up. That's not how it's done anymore. We're getting the oil that's very, very deep, the oil that's in between rock layers. Now, pollution, of course, carbon dioxide is, of course, one of our major pollutants. But other things, we know how to scrub some pollutants out, and hopefully we'll solve the carbon dioxide problem. And overpopulation, well, we do know how to solve a lot of that too. We just have to have the society that will use the technology. We have the technology to solve these problems. It's got to be society catches up though. Anyway, we'll be talking more about that. The next thing you're going to be doing is going to a metric system review. Okay, so see you later.